Howdy howdy, this is Mr. Potter. In our previous video we talked about the idea of a bubble sort, a way to sort the data so that our binary search would be more effective. And I mentioned that we would talk about a couple of other sorting techniques that would be more effective in that they took less time to actually process the sorts. And so the first one I want to talk about is this idea of a selection sort. So first thing I want to do is I want to talk about how exactly it's going to be different. So let's say that I've got a number 8, 1, 6, 7, and 2. If I'm looking at this list, I know that 8 is bigger than 1, so I should have to swap if this was a bubble sort. And then 8 is bigger than 6, so it would have to swap. And 8 is bigger than 7, so it would have to swap. And 8 is bigger than 2, so it would have to swap. That's how we did the bubble sort. But if I look at this list and I say, what is the smallest number on this list? You'd immediately be able to say that the smallest number on this list is 1. This is my smallest number. And the question is, which spot does it belong in? It belongs in this first spot. So the question is, instead of having to let 8 bubble its way up to the top, why don't we find the smallest number, find the spot it goes to, and just do that one swap? In other words, just swap the 8 and the 1. So I'd have 1, 8, 6, 7, 2. And I know you're thinking right now this is absolutely not different from what we did with the bubble sort, except I'm done with the first number. I know that this first number is in the right spot. So now I need to say, okay, what's the next smallest number? And I'm looking at this, and my next smallest number is this 2. And where do I want this 2 to go? Well, I want the 2 to go in the second spot. So let's swap. So if I swap, I get the 2 and the 8. Everything else stays the same. And I know that these numbers are in the correct spots. So now I need to ask myself, okay, what's the third smallest number? Well, it's here. It's the 6. And where does it belong? It belongs in this spot. Well, that's convenient. There's no swapping going on. So 1 and 2 and 6 are done. 7 and 8 follow for the ride. These numbers are all sorted. And now the next smallest goes in the next spot. Everything else follows for the ride. And the next smallest has to go into the next spot. And everything else stays for the ride. So notice that there were only 5 swaps that could happen. And also notice that the swaps didn't have to happen. There were several times when the number just never needed to change position. As a matter of fact, this situation here, the number will never have to change position. Because if these first 4 elements are in the correct spot, then this last element has to be in the right spot. So this is a different type of sort because you only have one swap per pass. The only reason that you're doing a swap is to get the smallest number in the right spot. To get the smallest number in the right spot. That's really the only reason that we're doing a swap at all. So let's try this with a little bit larger set. So I've got pi here. And the first thing I want to do is find the smallest number. So I'm looking 3. I think 3 might be the smallest number. No, 1 is smaller than that. I think this is the smallest number. Is 4 smaller? No. Is 1 smaller than 1? Well, no, 1 is not smaller than 1. This is still my smallest number. 5 doesn't work, 9 doesn't work, 2 doesn't work, 6 doesn't work, 5 doesn't work. This is my smallest number. This has to go into the first spot, and so I'm going to swap the 3 and the 1. So I have 1, 3, 4, 1, 5, 9, 2, 6, and 5. Then I look for the next smallest number. This is in the right spot, so I've got 3. 4 is not smaller. 1 is smaller. I think that might be my smallest number, but I have to check the rest of the numbers in my list, and 1 ends up being the smallest number, so we swap these numbers. So that means the 3 goes here, the 1 goes here. Everything else gets copied down. And I know that these first 2 numbers are in the right spot. So now I'm looking for the next smallest number. Well, I think it's 4. Nope, you know what? 3 is smaller than that. Yep. Nope, 2 is smaller than that. 2 ends up being the smallest number. The 2 and the 4 are going to have to swap. So I'm going to swap the 2, swap the 4, and everything else comes down for the ride. Now at this point, my first 3 numbers are in order. The key here is that I'm going to find the smallest and then swap. And notice that I'm only doing one swap per pass. The next time I swap, I'm going to need to keep this 3 because this is the smallest number, and it's actually going to stay. So these are my smallest numbers. And I've got 5, 9, 4, 6, and 5. So then we swap these. So that puts the 4 in the right spot. Then I'm going to swap these. So that's going to put the 5 in the right spot. Everything else drops down. Then I'm going to swap these. So the 5 is in the right spot. And then I've got 1, 1, 2, 3, 4, 5, 9, 6. And then I don't have to swap at all, so this is the correct sort. Notice that I only had to do 1, 2, 3. That was not a swap. 4, 5, 6, and there was no swaps here. So we had to do 6 swaps. 6 swaps. That's very quick. If you remember how we did in the bubble sort, we had probably 20 different swaps that had to take place. So this is a much more efficient way to sort. So let's take a look at what this looks like from a pseudocode standpoint. I still have to keep track of the length of the list. I still have to start at 0. But what I'm going to do is I'm going to keep track of my spot, and I'm going to keep track of my target. And so what I do is I say, okay, if the spot that I'm looking at is bigger than the target, then that means that my target that I'm looking at is my new spot, and I need to keep upping the ante. And so I'm going to keep doing this. Actually, that should be less than. And I'm going to keep doing this, and then once I've gone through here, I know that my target is hitting the smallest number, because it's got to be the smallest of all of these. So then I do a swap, but I'm swapping with the first spot, or the second spot, because pass is going to increment as well. So it's this idea that I'm going to find out what the smallest number is, and then swap it with the position I'm looking at. I start at position 0, and I find the smallest number, and then I swap those spots. Then I'm looking at position 1, I find the next smallest number, and I swap those spots. Then I'm looking at position 2, I find the next smallest number, and I swap those spots. That's how this sort works. So, the better question then is, what happens when we have a lot of repetition? So I've got Euler's number. If you've ever played on a calculator, this is your e to the x button whenever you type in a 1. So notice there's a lot of repetition here. So the very first thing that I have to do is I have to say, okay, starting at position 0, what's the first number that I see? Well, this 1. That's the smallest number I see. There is another 1 over here, but I really can't say that 1 is smaller than 1. So this is the one that gets swapped. The 1 and the 2 swap. Everything else drops down. Then I look, I know this is in the right spot, so now starting here, this is my spot, and I'm looking for a new target. So 2 works. That 2 isn't smaller than this 2, but this 1 is. This is now my target, and I'm going to swap. 1 and 7 swap. Everything else drops down. And now I know that these are in order. So now this is my new spot. That's a 2. 2's not less than 2. 2's not less than 2. So this doesn't change. And so now this 1, 1, and 2, these are all the same. And everything else drops down. Then I look for, this is my new spot. This ends up being my new target because this is smaller than 8, and this 2 isn't smaller than this 2. So we swap. And so this idea that whenever I have repetition, it's always the first one that I see that actually gets swapped. Now this 2 and this 8 will swap. So I have 1, 1, 2, 2, and the 8 and the 7 and the 8 drop. Then I'm looking at this spot here, and the 7 and the 8 swap. And again, I end up with a similar situation as before, where at this point, all I know is that these numbers are in order. But in reality, the list is done. The list is sorted. I'm going to need 3 more passes, or actually just 2 more passes, before I know that this sort is done. I have to do the 2 more passes. But notice that there are only 1 swap, 2 swaps, this wasn't a swap, 3 swaps, 4 swaps, 5 swaps. It only took 5 swaps to get this list in order. So again, we run into this question of what is our best case and what is our worst case? Well, let's take a look. Again, our best case is where we have the fewest swaps. And that's going to take care when we have no swaps. In other words, if our list is in order. If our list is in order, then I don't have to do any swaps in there. And that means that I'm going to ignore those 3 lines of code. Those 3 lines of code that add up every time that we have to do a swap. For our worst case, I want to have as many as possible. So then the question is, what if I was to have a thing like 9, 8, 7, 6, 5, 4, 3, 2, 1? Something that would have represented our worst case scenario for a bubble sort. Well, the first step is this 9 and this 1 are going to get swapped. The second step is that this 8 and this 2 are going to get swapped. The next step is the 7 and the 3 are going to get swapped. The next step is the 6 and the 4 are going to be swapped. And guess what? In what we thought was our worst case scenario for a bubble sort, we only have 4 swaps. In the case of our bubble sort, we would have had 56 swaps going on here, trying to make sure that all of these numbers got in the right spot at the right time. And 4 is much less than 56, so we end up with a much more efficient loop. As a matter of fact, what is the situation? That's the worst case here. The idea is that when I'm doing these swaps, I have to keep doing a swap every pass, but my worst case is that if I have 9 elements, my worst case is going to be 9 swaps. That one situation where I have 9 different swaps that I have to take care of, that's going to be my worst case situation. So what if I had something like this? 2, 3, 4, 5, 6, 7, 8, 9, and 1. Notice the first thing that's going to happen is 1 and 2 are going to swap, and everything else falls into place. Then I'm going to have the 2 and the 3 swap, and everything else falls into a place. So notice that my worst case situation is a list that's almost sorted. This situation is going to have 9 swaps, but the thing is, a bubble sort, which would have taken care of this in one pass, is also going to have 9 swaps. So notice that even our worst case scenario is still better than a bubble sort, or just as good as a bubble sort. So that's something to keep in mind, is that when we're talking about this selection sort, this is actually one of the better loops that we can deal with that's still running an n squared time, because I still have to go through this to make sure this number is correct, then go through this and make sure this number is correct, and then go through this and make sure this number is correct. So it's still going to take 81 passes, or as we say, 81 comparisons, to figure out exactly when this list is going to be sorted. But in the amount of code that actually gets run, we're severely decreasing the number of swaps that actually take place. Now, in our next video, we're going to talk about a different sorting technique. It's not necessarily more efficient if I have a lot of unsorted data, but we'll actually see that it works very well in very specific cases. That's where we're headed for next time. So, once again, this is Mr. Potter. Thank you for watching. Have a great day.